Look, I'm going to tell you something which perhaps isn't often expressed. You know, as a scientist, we're meant to be data-driven, cold-hearted, analytical. But there are fads and there are fashions in science, as there are in all aspects of life. And right now, microplastics is what we would call a hot topic. The question is, why? And what do you believe the evidence that has been presented to you in the newspapers, in the popular media, is really telling us about the true risks? Because I think it's perhaps not as simple as people think. Now, I work in a department, we have a microplastics group, and so when I told them I was going to talk about microplastics after they'd taken me out of a headlock, they gave me permission to say things. And so I wondered, well, there was the last piece of interaction they had talking about microplastics with a member of the popular science media. And my colleague, Dr. Stephanie Wright, had just been speaking to The Guardian, and so this is quite current. This is from the esteemed journal, the Health and Wellbeing section of The Guardian, and it's about microplastics, and look, it says they're everywhere. They live in our laundry bins. You can find them in the Mariana Trench. They're in the human bloodstream. They're small enough to infiltrate every biological barrier, such as the gut, skin, and the placenta. We are now partially plastic. But how worried should we be? And is there any way to minimize the exposure? Well, I think if you were to believe all of those statements, you would be quite entitled to be, quite frankly, terrified. But not all of those things are solid facts. Many of those things are suppositions. They are inferences made from very preliminary data in a new field. And I think it's worth, therefore, to step back and to actually look at where the evidence came from and what the evidence really is, and to potentially put a bit more balance into this debate. And there's a reason for this. I come not to sort of like murder microplastic research. I personally feel that the way it's being presented at the present moment in time could cause it quite a lot of reputational damage before the questions which need to be actually answered have been properly configured. I think we have to be extremely careful going forward. Now, let's think about this. Let's get everything set out. We absolutely have a global problem with waste, yes? We absolutely have a massive ecological problem with plastics, macroplastics, and plastics breaking down within our waterways, within our oceans. Absolutely. But it's not really where most of it is. And that's something which I don't think is fully appreciated. Most of the plastic that has been manufactured, predominantly really since the 1950s onward, when there was an explosion in production, is in landfill. Only a minority of that material is actually in our oceans. So when you see the information in the ocean, when you see images of sort of like turtles and dolphins and whales swimming with plastic bags, you're looking at only part of the problem. Now, I've got a figure here of, let me think, it's 5 billion tons of plastic waste in landfill since 2015. That number is projected to be 33 billion tons by 2050. Which has become the international unit of date when all things are now going to be judged. Yes, 2050, look at 2050. This is a situation which is only getting worse. And as I said, we're only looking at part of it. Now, the issue is when the plastic enters the terrestrial, the aquatic systems, it begins to break down, but very slowly. The very properties which make plastic such useful materials, their durability, their heat resistance, and their strength, means that they persist and they slowly break down. They gradually fragment into smaller and smaller particles. And this leads us to what the definition is of a microplastic. And I'm going to be upfront and say I have massive problems with the terminology used within the microplastic field. And I can define this quite straightforward. What is a microplastic? A solid, synthetic, polymeric particle of no more than 5 millimeters on its longest dimension. That doesn't sound very micro to me. In fact, the nanoplastics is defined as being less in that one axis as 1 micrometer, which doesn't sound very nano to me either. So the way in which micro and nanoparticles are described within the environmental space is very different to the way in which I, as a sort of environmental toxicologist, think about particles and fibers in the human body, where a nanoparticle is less than 100 nanometers and a microparticle is genuinely, if it's going to be inhaled, less than 2.5 microns. This really matters in the way in which this debate moves forward. Now, where does it begin? And this is one of those, I always like taking you to the pivotal paper, yes? This is the paper which first sets out the problem of microplastics and why the focus is predominantly in the oceans for the first part of the debate. It's published by Richard Thompson. He's an academic from the University of Plymouth. He's not the member of Fairport Convention, that's a different guy. And this paper is really important. If you look very carefully, just down here, and you get down to this point, you'll see the first ever mention of microplastics in any paper in the literature. And this is one of those wonderfully elegant, very short papers where they do something very simple. He notices there's plastic in estuaries on the shoreline, and so he just collects samples and he analyzes them. And he analyzes them to see if he can see small plastic debris. And then to try to determine what it is, he uses a technique called Fourier infrared spectroscopy. And at the top in the dotted line here, we have a little particle he's identified within the sediment. Beneath it, you have pure nylon. And you can see it's like a fingerprint, yes? You can see the similarity. So he's identified that there's a nylon particle, and it's in the samples. And in fact, he identifies 9 other polymers, particles within those samples. So then he goes back and discovers, well, they've got samples, plankton samples, which have been stored since the 1960s, and he looks in those samples to get a 1960s, 70s, 80s, and 90s sample, and you can see the amount of microplastic within those samples is increasing over time. So there is something accumulating in our aquatic system. And then he does something which nobody ever quotes in this paper because it's in the supplement, and so nobody ever looks at it. He takes some filter feeders, polychaete worms, barnacles, some amphipods, and he feeds them some plastic materials, and they eat it. First evidence, therefore, that microplastics in the aquatic environment will be taken up into species and enter the food chain. And after this, well, you can guess what happens. They go out, people look in mussels, they look in shrimp, they look in fish. We begin to see how the microplastics are accumulating within aquatic species, and particularly those species which end up on our dinner plates, yes? So we begin to develop an interest in that area. And that leads us to this explosion. We begin to see this, and I've just taken a range of things here. Look, these are very interesting headlines. 7,000 particles a day, microplastics in the deep lungs, raining snow in the ocean. I can go through some of these. Microplastics detected in meat, milk, blood, farm animals, microplastics in your blood. I mean, not all of your blood and not consistently in the same individual in the study, but nevertheless, it's there, it's been reported. Did you know in a week you eat a credit card's worth of plastic? Okay? It's interesting, isn't it? And this is interesting because now we're beginning to, it's got to the point in the press that we're in the point of infographics, yes? It's become such solid fact that we can talk about the different type of microplastics, and we can actually demonstrate that once inside the body, they affect your hormones and your health, your lungs, your kidneys, your intestines, and your placenta. This is delivered as fact, and very little of it is more than inference, and some of it is palpably incorrect, has been challenged, has been shown to be wrong. So, when did it all start? This is a bit strange, isn't it? Why show a picture of Chatterton by Henry Wallace in 1855? The reason I picked this picture, well, I work in environmental poisoning, so he's just killed himself with arsenic, so there's kind of a link there, an old-fashioned poison, talking about environmental poison. But the first synthetic plastic was created in 1856, which means you're looking at a picture painted representing a time when there were no synthetic plastics in the world. There were polymers. Let us not forget there are polymers. This picture's full of polymers. We have a cotton shirt, we have silk, we have some plant up there, some lignin and cellulose. So we have biological polymers, but we don't have synthetic polymers. This is the era before plastics, and it's not a very long time ago when you really think about it. So how did it all change, and what is to blame for this sudden transition to plastic and the way that we hyperproduce plastic? And I've got a surprise for you because it's two things I suspect you would never have guessed. The two evils are snooker and hairdressing, or hair care, vanity and recreation. By the middle of the 19th century, there was an explosion in the popularity of billiards and snooker. And where were they getting the raw materials from? Elephants. And they were almost extinct. They were running out of capacity to meet the demand for the material to make snooker and billiard balls. Over here, we have a tortoiseshell comb made from the hawksbill turtle, almost driven to extinction at this point in time. So there was a material shortage, and people were desperate to find alternative malleable materials that could be employed to deal with consumer demand. And then in come our three brave knights to save the day. The fourth one is coming in reserve, sort of the D'Artagnan of the pair. The first synthetic, not fully, partially synthetic plastic was developed by Alexander Parkes in 1856. It's based on a cellulose nitrate. So bizarrely, they're using natural materials to make moldable plastics, yes, reacting it with plasticizing agents such as camphor, vegetable oil, chlorophyll, so forth. And he develops his malleable material, which can be molded to make products, yes, but it's not great. It's quite brittle, yes. Certainly you can't make billiard balls from it, yes. They do make combs from it. If you go to the Science Museum, you can see some of the materials from Parkson. He has a business partner because this guy is a bit sort of like, well, you know, he's an inventor. He's not going to make a success of his business. This guy, his partner, decides he's going to take that Parkson site and move to a new compound, just a different configuration. And again, he gets a much more durable compound, but it's still not really working. The really big development comes on the other side of the pond, when John Wesley Hyatt perfects the mechanism of making what effectively is celluloid. Yes? So he makes celluloid by taking the principles started by Alexander Parkes, but kind of replicating them under pressure in a much more industrialized process, so that we begin to have celluloid film. So celluloid combs begin to appear. Consumer products in celluloid begin to appear. And of course, one other thing which happens is we begin to have films. And there is a wonderful story, because in one of the early films, one of the actresses cuts her hair short. And every woman in the world who goes to the cinema decides to cut her hair short, and the comb market collapses internationally. To deal with the collapse of the market for synthetic celluloid combs, they divert interest to sunglasses. And sunglasses begin to be promoted through the films, and the plastic gets used in that respect. But these guys are right there at the beginning, not perfect, because really the next stage is when we begin to see mechanization. All of this is really still based on natural materials, and we get back to why that might be important earlier on. But by the time you get to the end of the century, a sort of alliance is beginning to be formed between people who realize the potential of plastics and the oil and petroleum companies who have waste product they want to monetize. This really begins to then become realized with the invention, well, this is the patent in 1909 of Bakelite, the miracle material that could be molded to make everything from radios to door switches to toys. And this begins the first real commercialization of plastics. So we're getting somewhere now. We're beginning to see plastic manufacturing taking off within the United Kingdom with marketing campaigns to promote the purchase of this material. And in come the big boys. We begin to then see the chemical companies invest, and we begin to see some of the polymer names we're all very familiar with. DuPont developed neoprene in 1931, nylon in 1935, just in time for the Second World War. Polyester 1950, Kevlar 1965. ICI developed perspex and polyethylene, ethylene gas being a byproduct of the oil industry, so therefore taking a waste product and converting a product for it. Dow in 1954 developed polystyrene. So we begin to see the diversification now into sort of very, very significant products. But the real thing which kickstarts this, the real thing which really kickstarts the plastic, if you like, consumer boom, is World War II. Plastics play a key role. Huge manufacturing capacity is built up to deliver plastic components, particularly for the aviation fuel, the aviation sector, plexiglass, whole hosts of plastic components for the aircraft. So this is built up, massive capacity, the war ends, and they have capacity and nothing to do with it. So they have to innovate, and they have to innovate into the only market which is going to be able to replace that, and that's consumer products. And so we begin to see a pivoting towards selling people plastic commodities, and they do an exceptionally good job at it. I think the adverts I'm going to show you now, taken from the 1950s through to the 1960s, are really interesting, viewed in hindsight, in terms of the concerns and anxieties we currently have about plastics in our environment. Cellophane is wonderful. You could wrap your baby in it, protect it from the dangerous hazards, germs, and viruses. Nylon has taken off, great success. Tupperware is launched with a fantastic marketing campaign in order to encourage people, almost by peer pressure, to purchase the material. Plastic's not only a great new innovative problem, it's the American way of life. You invest in this because this is the brave new dawn. This is our new future. It's great because you can spill things on your shirt. Your clothes are washable for the first time. And you know what? They celebrate single-use plastics. Away with tiresome cleaning and disposal. You can just throw this stuff away. It's a real innovation, yes? So all of a sudden, we have an absolute explosion in plastic use. A huge explosion, not just in Europe, but globally. Now, some of this you're not going to be able to see. I know, I appreciate it. I've put this together. But what I wanted to do was just to say, okay, so we've set the scene, okay? We've gone from nothing in the mid-1800s, yes, to a huge industry making plastic goods across multiple sectors, yes? And we have lots of plastics and lots of different types of plastics, and I talked about microplastics. So look, here's some little bits of terminology because they will become important as we go through it. People like classifying things. So what do we have? We have plastic fibers like polyamide, polyester, polypropylene, thermosets, these like epoxy resin. These These can be molded, thermoplastic, semi-crystalline, amorphous, and then we have elastomers. And the reason I put elastomers at the end here is there's a big debate about whether they should be included in the definition of microplastics. The field is split 50-50 about whether they should be part of the ban. And that becomes very important as we go through the remainder of this presentation. Now, let's go back to water. As we begin to see this increase in consumer purchasing of plastics, we begin to see an increase in plastic waste. And what's really interesting is it begins to actually enter what you may think of as our fossil record. I don't like the term, but it's the term which has been used within the literature. So here we have a grey line, and that grey line represents the world plastic production in tons, and the dotted line represents the number of plastic particles recovered from oceanic sediments over time. So what you're beginning to see is plastic use on land is manifesting as a significant accumulation of plastics within our oceans, and you can see the dates work perfectly. 1915, 1916, 1980, 1990, and then bang, 2010, when globalization kicks in, and we have the new economies from Southeast Asia taking off, then we begin to see huge amounts of plastic production. And this has resulted in some people deciding that we live in the plastic age and coming up with a terrible term, the plasticine. So the plasticine, I spent a long time having debates with people about the anthropocene and when the anthropocene begins, yes? Is it the CO2 dip because of smallpox? Is it radionuclei being released in the atomic explosions? Is it the plastic appearing in sediments? I think it's very academic. Let's just assume, okay, that irregardless of where you think the Anthropocene or the Plasticine began, we're resolutely in the middle of it now. There is no question that we're past the point at which we have shaped and are having a significant impact on our planet. It's not just in places that you think you're going to find it. So it's quite easy, isn't it? It's in the oceans, it's going to be taken up into filter feeders, it's going to be taken up, therefore, into fish, and then we might eat it, it's going to enter our food. People understand that. One of the interesting things which has emerged, certainly over the last 10 years, is it's in our air as well. Yes? And there are multiple studies. These little dots here, the black dots, represent places where people have done studies where they've looked at microplastics within the air that you breathe. And this is important because it means there's another way in which potentially plastics can enter your body, yes, via your inhalation. And here are some numbers, and the numbers are important. I'll go through them very carefully because I want to kind of contextualize them so you can begin to think about things in context. Paris, Dongguan, China, Hamburg, Pyrenees on top of a mountain, London. We have a range of particles expressed usually per meter cubed per day. They are usually particles depositing, yes, just passively into a sample. Very few of the studies have actually sampled air pollution, using size-selected mechanisms to look at PM10 or PM2.5. But it's definitely in the air, and it can be characterized, and it can be confirmed chemically as being a microplastic. So it is there, but there's not very much of it. To give you a context, if you were standing next to the road outside, the concentration of total particles in a cubic centimeter of air would be between 20 and 40,000 per cubic centimeter, versus something in the order of 30 through to maybe 500 particles per day, yes? So bear in mind that they're there, but they're not there in tremendous abundance, yes? Doesn't mean they're not important, but there's more other stuff in the air that we breathe than there is plastic. And if you actually look at the literature and you break it down, and I've taken this from a review published in 2012, what you can see is when you look at those particles and you look at the papers which have been published, it's mostly big stuff in the air because nobody's got around to measuring the small stuff in the air, the stuff that you would actually breathe and would get into your lungs. That's a bit of a missing gap. And what you tend to find is small fragments, but you also find fibers. Yes, there's quite a lot of fibers, and many of the fibers you find in outdoor air look as though they come from textiles. Yes, they're sort of textile-derived materials. And you can see that we have polyethylene, and we have PET, and we have acrylic. And so we can begin to identify that they are in the environment. And how do they get there? From a variety of sources. Landfill itself, the particles are breaking down, wind's resuspension of particles. Actually, a lot of it gets into waste in slurry, and then it gets spread on our fields in sort of like spraying. That aerosolizes it into the atmosphere. We get quite a lot from tire wear, and that's when it gets confusing, because tire wear is kind of an elastomer, or is it not? Is it a microplastic? We'll get onto that in a second. And you can even show evidence of it being re-aerosolized from the oceans and deposited in sea spray inland. So there are many sources by which these particles, plastic particles and fibers get into the air, but there is a gap. And here's the gap. The assumption is there's stuff in the air, we breathe it. The stuff which has been measured in the air is big, too big to be really a significant respiratory hazard. What has not been measured in the air is the small stuff. And the reason it's not been measured is because analytically it's really difficult to measure small plastic particles. You're right at the very edge of the technology which is available at this time. But it means the evidence isn't really there. There is a massive yawning data gap. Okay? Doesn't mean it won't be closed at some point when the technology catches up. But at the moment, the assumption is, because we can see the bigger stuff, the smaller stuff must be there. We just can't see it at this present moment in time. Let's look at other stuff, because you can begin to then work out what we have in a whole range of things, and I've put them down here. Bottled water, shellfish, salt, air. You can work out depositions. You can begin to work out the number of particles you take up per year, and you can get really big numbers, like you take up 1.5 million particles, plastic particles, through various forms a year. And the other thing you have to bear in mind, that's probably true, but it's not actually a scary number at all, because most of the stuff which goes into your gut comes out in your feces. Yeah? Almost all of it. What goes in, goes out. And there are very good reasons for why that's the case, and we'll talk about that in a second. Here I have a whole host of other things where people have measured particles, and we can go through the list. Seaweed, salt, of course, sugar, honey, indoor air, outdoor air, tap water. This is the only one which I think is worth your attention. All of the ones at the top are around, they're in the hundreds to thousands, and we get down here and we get 12 times 10 to the 9 microparticles per cup of tea. Yes? These are those lovely synthetic plastic bags you get, yes? Little nylon bags, which are very good. Put that in hot water, you create the perfect environment for the release of microplastics. To the extent that, to be quite frank, if I wanted to do a study on microplastic uptake and health effects on a population, I would probably attempt to do it using tea drinkers, yes, because they're the individuals who would have the highest concentrations. This is, again, just for completeness, to say, look, it's in the ocean, it's in outdoor air, quite a lot of it's indoors, yes? There's quite a lot of this material, again, quite big indoors, from clothing, from your carpets, yes, from general goods and resuspension of dust in the household. So we have a huge amount of material there. And again, this is just to say some of it's very short and circular, some of it's quite long. But it's important to bear in mind when people talk about microplastic particles, what they actually are talking about are microplastic particles and fibers. The fibers are equally important. Fibers are really important for a number of reasons because of how they're measured and how they interact with your airway. And here I can explain why. It's difficult to chemically characterize microplastic compositions. The technology, Raman spectroscopy, inferred spectroscopy, aren't great at the very, very small sizes of particles, but you can look at them by SEM and TEM, and you can quantify them. When you do that, you can see there are very, very small fibers, and if you look at the end of this fiber, it looks as though it's just falling apart. Yes, it's beginning to disassociate. So you can see it's going to break down into smaller particles. And so there are studies demonstrating that you can visualize really, really small particles, but they are mostly fibers, yes? And then the important thing about a fiber is it doesn't really matter how long that fiber is. The way in which it deposits in your airway is based on its diameter if it's rigid, yes? They kind of align with your airstream a bit like a javelin. So when they go in, and your body, they deposit in your airway based on the diameter, not the length, yes? Which means that some of these are important, and that's about as good as the evidence gets for saying there's really small particles in the air and we should be concerned about them. Okay. What happens when we breathe them? Well, we have to think about their fate. So we know we eat them, and we know we drink them, and there's this perception, and I think everybody absolutely takes it as read. They've read that microplastic particles get into your blood, therefore they must get into your lungs, they must get into your gut, they must translocate into your circulation. And people have reported that they're within organ systems, within your liver, within your lung, and people are desperately trying to find them in the brain at the present moment in time for a high-impact publication. But we just have to pause and reflect that the body is really good at keeping stuff out. We usually have very, very good barrier function, and the evidence is really early. And I can give you an illustration of that the evidence is early so that you can kind of titrate your expectations. So one of the things which is really often said is that there's evidence that you can see microplastics in the placenta. This is the evidence. It is here, in this panel. You'll see these little squares, and they have little kind of like, there's a sort of yellow and a blue and a green, sort of like, almost like a rock. It's a study which took 6 placentas, whole placentas, and digested them, and then filtered them, and then took the extract and then concentrated it to see if it could see anything which could not be digested by potassium hydroxide in the system, and then it looked at them. In 4 placentas, nothing. 2 placentas, nothing, and the rest definitely were. And this is all they show. These are all of the particles. These are Raman spectra, which again are a bit like a fingerprint. They tell you something about what the actual material is. Of these, only 2 or 3 have been formally identified as a microplastic. Many have been identified indirectly because they have colorants which are associated with microplastic or polymer manufacture. So I would say there's some evidence, but this is why I'm always really cautious about microplastic research. We live in a cloud of materials. There is no more plastic-enriched environment than a hospital. Just moving around a hospital, transferring samples to a hospital, taking them to your lab, processing your sample means that you're likely to get contamination in any of your samples. And it's going to be really challenging to absolutely confirm that these are real in a tissue which has been digested as opposed to potentially an artifact. It doesn't mean I don't think they've done a really good job. I think in this paper they did as well as anybody has done. It's just that it's very subject to artifacts, and that's a problem within the entire field. If you do breathe or take in a particle, in order for it to enter the blood, in order for it to be distributed around the body, to go to lymph nodes, potentially to go to organ systems of the placenta, then you have barriers. You have the gut barrier, and you have the upper and the lower airway barriers. But these are pretty good at keeping stuff out, to be quite frank. I gave a lecture last year. I talked about the barrier function. And actually, in both the upper gut and in the lower airways, you have a mucus blanket, which is incredibly effective at capturing large particles and ensuring that they don't actually get taken up into the tissue. Now, there are potential routes by which they could enter the circulation. They could be taken up into phagocytic cells and translocated across the epithelium into the blood. And there are gaps and there are regions within the gut which promote particle uptake. But the evidence is not there yet, okay? Possibilities, not direct evidence. And this is just to make the point, because I think we often forget, even if we breathed it, and there was a lot of it, even if we ate it and it went into our stomach, the particle sizes they have located within food and within air are too big, quite frankly, to be responsible to enter the body. So again, we have a gap. We have plausibility, people detecting things in tissues, but it doesn't add up. It's not quite as coherent a picture as I think people would like us to see. So this is where we are. This is my timeline, okay? So 1950s, mass production begins. 2004, that's when we have the identification in water and the term microplastics. Then we have, they're identified in various places, selfish, short, atmospheric fallout. Yes, people begin to look in human stools to see that most of the stuff which goes in comes out, and that's pretty good news, I would argue. And then what happens? What happens after that is the hunt is on in every tissue and every body fluid that you can lay your hands on to demonstrate that you can identify a microplastic or polymer within it. And that becomes pretty dangerous science, because the presence of a chemical, or specifically the presence of a chemical-physical entity, which is a chemical within a tissue, does not simplistically equate to pathology or to a health effect, yes? It's only part of the question. It only demonstrates that there is the feasibility of getting there. And anyway, if we have had an explosion in plastic production since the 1950s, where are all the health effects? Why have we not picked up on them? What is the reason for this? And that takes me to this issue, myth or menace. And I really think there are considerable health risks. I think there's a lot of misunderstanding in this field and a lot of very poor reporting of associations. And I can tell you why. Let's just focus on breathing stuff for a moment. I work on air pollution, and we breathe a lot of stuff, yes? And we already know that the stuff that we breathe globally causes 4.2 million excess deaths in outdoor air and 3.8 million deaths each year in indoor air. So that's a lot of people who are dying of the stuff that we know they're breathing, which is defined as PM2.5. So if the microplastics are in PM2.5, technically we've been studying it, but we don't know how much of that burden is attributable to it, because we don't know how much is in PM2.5. We can infer from the measurements of suspended particles in the atmosphere that it should be less than 1%. Yeah? Not as much as you would think. But we do know that particles are bad for you. What we don't know is whether the microplastic particles are bad for you, because there are absolutely no health studies. None. There are no health studies demonstrating that microplastics are bad for your health in the literature. This PM2.5 comes from various places, and I've illustrated here a bit from tire wear, a bit from brake wear. So that tire wear thing, that is going to become important as we go through this. But most of the PM2.5 is other stuff, yes? So why do we focus so much on microplastics and not on the other stuff? It's something which I spend a lot of time thinking about. And even if we demonstrated that particles were entering the body, this is the important equation, yes? Things may be hazardous at a high concentration, but if you're not exposed to a huge amount of it, it's unlikely to produce a particularly high risk to health. And we would love to do that equation for microplastics, and we do not have the data to do it. It simply does not exist at the present moment in time. Added to which, this question easily becomes unanswerable very, very quickly. There are many types of microplastics, many different materials, polypropylene, polystyrene, polyethylene, a whole host of materials. They are manufactured with additives. So it's the material plus the additive. They come in all different shapes and sizes. They have all different functionalities. So even though we have a small amount of the stuff is really heterogeneous chemically and in physical form. And then, once it's in the environment, if we're concerned about it breaking down in the environment, lots of stuff can happen to it. A particle which is broken down in the environment will be coated with chemicals and entities within the environment, bacteria, polyaromatic hydrocarbons, humic acids, fumic acids. So just being in the environment means that it's no longer just a pristine plastic. It is an entity, a carrier of things within the environment. How do you begin to unpick that in terms of a health study? It's almost got too many dimensions to it to have a really simple question. You have to really begin to simplify the question you're asking. And at the moment, people, I think, are trying to be far too ambitious. So, again, the outside world decorates particles and fibers. When they enter your body, they become decorated with the molecules within your body. This is really complicated stuff. But there are hints. Whenever I think there is no hope, Monday through to Friday mostly, what I do is I go to the occupational health literature. Because in the occupational health literature, you have the people who are exposed to the greatest concentrations of a particular entity. And there are individuals who work within the flocking industry, which is where they take plastics, usually nylon, and they make very, very small fibrils, which can then be used as insulation. And what you're looking at here is this is a flocking factory, and you can actually see the amount of material in the air, and that's just an illustration of the flocking. What we know is that people who work in that industry have high rates of interstitial lung disease. They have significantly more lung disease. They have idiopathic fibrosis. They have scarring within the airways. It doesn't matter, you can see the same pathologies if it's working in polyethylene or polypropylene or rayon. It seems to be pretty consistent. So at high concentrations, this plastic stuff in the lung seems to trigger a response which leads to lung scarring. The concentrations in these factories are off the scale, 2.2 milligrams per meter cubed. So to be quite frank, if you can't demonstrate an adverse effect of microplastics in these environments, you can forget it, because that's really quite bad. And you can begin to look pathologically. You can show the lungs are inflamed. They have granulomas, which is like a tissue response to try to sort of like encapsulate irritating material. And you can see scar tissue. So they will cause harm at the right dose, at a very high concentration. And that should focus our attention on what we should be looking at. And at this point, I think that we would benefit from just stepping outside thinking about microplastics per se to talking about the fact that if microplastics are doing this, it's because they're biologically persistent in the body, and they're not the only things we breathe or eat which are biologically persistent. And there's a very wide literature on particle fiber toxicology, silicates, for example. And we know many of the pathways which are likely to be important if these things are having an adverse effect. We know that fibers seem to be a little bit more difficult for the body to deal with than small particles, because it's very difficult for phagocytic cells to remove them. We know that transition metals are bad. We know that surface charge matters. We know that the uptake of toxicants. So we have a kind of picture emerging. We can go back. And then this is something I should never show in a public lecture, but I'm going to do it anyway, yes? If you want to demonstrate something, you need to have a pathway that you can test, yes? I think that it's going to be very difficult to show the effects of microplastics, but we do know that in extreme situations, it causes an adverse response, which is fibrosis and scarring in the airway. And then AOP is an adverse outcome pathway, which is a scheme you can test. And this says, the first initiating event is particle lands, should we say, in the airway, gets taken up, causes a macrophage to release inflammatory mediators. That triggers an inflammatory response, causes injury, moves to chronic inflammation, activates fibroblasts, results in scar tissue formation, ultimately leading to lung fibrosis. That is testable. You can develop models and tests to determine if you can do that. But if you don't have that adverse outcome pathway plotted, you are doing really very sporadic stuff. And I've looked across the toxicological literature in microplastics, and it is pretty poor at the present moment in time, early days, but not even with proper dose-response curves or with very clear hypotheses attached to it. You still have that question. What on earth do you look at? Which particles and at what doses? Still don't know. Now, I don't know what the time is. Am I running out of time? I'm fine. Good. Timing is great. This came out very recently. I've talked about the plastics, but whilst we argue about whether the plastic polymers are toxic, we know that they are made with lots of additives. And this report came out from the UN Environment Programme this year. And it just did a review of the additives added to plastics at various points in their manufacture, those which are incorporated with them. Now, this is really important because additives don't covalently bond to the polymer. So if they're within the material and they enter a biological compartment, they will leach out, yes? We are obsessed with the particles. I think we have forgotten to worry about the chemicals that these particles carry into the body. And you can go through them, and we have quite a nice list of plasticizers, phthalates, chlorinated parafilms, fillers, mica, talc, clay, flame retardants, colorants, antioxidants, stabilizers, biocides, antistatic agents. I can't help thinking that we should have been looking over here for a while, because bizarrely, whilst there's not much literature which is sound and robust on the polymers, there's a huge amount of chemical information over here on the hazard of those particular chemical species. In this review, they identify 13,000 chemicals associated with plastics. 7,000 have been identified as having hazard. Doesn't mean they will cause damage. It means they have the potential at a certain concentration to cause an adverse response. Of that 7,000, they would conclude that 3,200 are of potential concern, need further study. And here we just have the list. It's the list I mentioned before, but there are some interesting ones here because it will pick up my later lectures, because we do have the forever chemicals, and we do have metals including lead. Lead is still used in plastic manufacturing, hard though that is to believe. We still do have all these UV stabilizers. So it's really important that we begin to extend our logic, because many of these compounds actually are linked to diseases, actually do have pathways. Many of them are endocrine disruptors. They do cause abnormal hormonal responses. They are associated with reduced fertility, and we have taken our eye off the ball, I think, by thinking only of particles and fibers and not thinking as chemical toxicologists in the round. However, it all still boils down to how much. It all boils down to the dose. And again, you have to make sure that the public understand that everything is a poison at an appropriate dose. Are the concentrations of things which are hazardous at a level that we're exposed to them actually likely to cause us harm? We need a very serious conversation about it. Now, tires. Tires are an interesting thing, because once you've realized that actually within the air there aren't that many microplastics, you kind of need to find something to study where there are lots of potential fibers and plastics, and you're looking at it right now. Tire wear, this is the important figure. I told you, the differences in particle numbers. Tire wear contributes 7.4 and 8.5 of all UK primary PM2.5, that's respirable, and PM10, that will also land in the airway. Oh, hang on, now this is interesting. Now we have something, potentially, which has microplastics in its broadest sense, which may have enough material within the air we breathe for us to be actually concerned with, and we can visualize it. So should we be focusing our attention here a bit more? And actually, what's really nice about this is because there's an emission factor, we can work out what tire wear emissions are. We can actually produce global models of tire wear. And when you have global models of tire wear, you can begin to do epidemiology and look to see whether the tire wear is associated with adverse effects in large groups of people. It's not perfect. There are lots of potential problems with this. Now, I told you that half the field thinks that tire wear is a microplastic and half the field doesn't. The people who study microplastics think it's a microplastic. The people who study tire wear think it's something else, yes? It's a bit territorial, it's not terribly healthy, but there is a reason for it, because tires are compositionally incredibly heterogeneous. This is an average if such a thing even exists. When you look into tires, it's like the Wild West, it really is. This is kind of what you have in a tire. We have some natural rubber, good, we can count that. We have some synthetic polymers, we have fillers. A lot of the fillers are carbon black, elemental carbon, stuck in there. So a lot of the particles by the side of the road don't come from the exhaust, they actually come from tires. We have some steel. We have antioxidants which are added in the actual vulcanization process so the tires can be manufactured. So tire wear is not simplistically microplastics, hence the resistance of the people who work in tire wear to allow people to call it that, yes? But a proportion of it is. And understanding what the proportion of it is really matters. And there are potentially ways you can do that. Measuring polymers in tire wear, we've spent the summer trying to do that, was quite challenging, but you can measure some of the antioxidants which are added in the manufacturing process, and you can use those as a proxy. So we're beginning to get somewhere that we could potentially move towards understanding what fraction of what we call tire wear actually we can call microplastics, and then we can do stuff, yes? Then we're beginning to actually think about something. Now, context. I think at the end of this I would go, microplastics, go away. Bear in mind, new field, lots of opportunity for young researchers to make big discoveries because there are lots and lots of gaps. But the problem is bigger, much bigger than plastics. This is a paper which was published in 2020, and it's one of those papers that when I read it, it recalibrated my view of the universe. Absolutely. And I'd like to see exactly how this works for you. We start in 1990, we go to 2020. This is a study which is looking at natural stuff in the world versus the stuff humans have made. Here we have concrete, aggregates, bricks, asphalt, metals, and a little yellow slip here, just at the top, right at the top there, which represents all the other stuff, including plastics. It's not the biggest layer by any stretch of the imagination. What this shows is that about now, 2020, plus or minus 6 years, there is now more man-made material on Earth than there is biological material across all domains. Bacteria, megaflora, oceanic, trees, vegetation. The world is now mostly man-made. And that means most of that at some point, unless it can be recycled and reused, becomes waste. So when we present information about microplastics, we have to see this in the round, yes? This is not something to be sniffed at. This is really amazingly concerning. Even taking out the chemical complexity and the health, that made me sort of stand up and wonder what was going on. And look, I mean, they've got these lovely infographics in the paper. You can look at it yourself. But there's more plastic than there are animals by mass on the planet. Just unbelievable. This is buried further in it. It's got the data in a slightly way. In the previous graph, it's in dry weight. This is in wet weight. And this is looking at anthropogenic mass and waste mass. And look at how the actual waste curve goes on. This is a crisis, yes? As big as all the other crises. I know we're not short of crises at the present moment in terms of biodiversity and climate, but this cannot go on. This is completely unsustainable before we even begin to think about the wider impacts this will have on health. And I didn't expect to see these graphs, and I work in this area, so even I was taken aback when I looked at it. Because this is our reality. We have made huge amounts of waste. And we made quite a lot of it during the COVID lockdowns. Those masks are all synthetic fibers, which are now in landfill sites, along with all your test and trace kits and all the plastic that was used in those things. Actually, there is a COVID plastic waste signature which has actually been studied by a number of people. And why this matters is we have all these conversations about the circular economy. And It's very idealized, and there are some complexities. We make it, we manufacture it, we reuse it. But there are complexities. The way we make things at the moment means that much of it cannot be recycled because of the additives which are used within it. Or when we recycle, what we do is we recycle toxic additives back into the plastic chain. But the shameful thing is that most of it doesn't get reused and recycled. Most of it gets sent to landfill site, or it gets burnt. And we export it. The solution of the developed world is to export our waste problem overseas. That, I would argue, is not good global leadership. It's certainly not good global citizenship. So if we're really going to be worried about the health effects of microplastics, I would be starting in Indonesia and the Philippines and in the countries where we are shifting huge plastic waste and where much of it is actually being burnt in open fires to get rid of it. I've got a figure here because people have begun to study this. These are looking at plastic chemicals which are released from burning. And actually, if you go, this is actually Dhaka in Bangladesh. You can see these are seasonal samples. You can see evidence of the plastic burning going on. So I think that's a little bit more alarming than a bit of resuspension and a bit of microplastics in your scallop in Sainsbury's, to be quite frank. This is really worrying in terms of just the way in which our planet works. And look at this. 91% of plastics produced have not been recycled. Look at the curve. 91% of the stuff which there is now probably more of than there is organic life. Less than 3% of plastics in the UK are from locally recycled plastics. Most ends up in landfill, is incinerated, or magically disappears somewhere else as part of our plan to deal with waste. Now, that's all very negative. And when I decided to do microplastics, in the back of my mind, I remembered this book. Yes, I had this book as a child, okay? The Story of Plastics, and I found it. Yes, the internet is a wonderful thing. And I just thought it was interesting, just looking back here, just for a bit of context. This is published in 1972, and it's published with the plastics industry. So it does have a very positive message, but it is for children, yes? And you can go through there, you can look at the plastic age, and it goes through all the things I've talked about today. This is probably more useful than my talk, and the pictures are better. And you get right to the bottom, and it goes to the future. And the future in 1972 wasn't bleak, yes? It wasn't, we're destroying the planet, we're all going to die. It was spaceships and monorails and domes, and it was great. Plastic was going to, and I was flicking through this book and I was going, well, where's the health section? Well, there's nothing on environmental contamination. What were we teaching the children back in 1972? That's the question I'd like to ask. Now, I was dared. Somebody said, nobody can go through a talk on microplastics and not have a picture of a turtle swimming in water with plastic bags. And I said, I won't do it, and then I have done it, and I've done it for a very simple reason. Because right at the end of this, I was thinking about this. Solutions and undue consequences. The reason that turtle is swimming in water full of plastic debris is because somebody tried to save the hawksbill turtle from extinction because of the comb industry, and innovated a solution to make plastics which kick-started the plastic revolution. So as we talk about innovations and solutions, especially solutions which are based about the repurposing and reuse of waste, bear in mind that history has many examples where the solution has ended up causing as many, if not more, problems than the thing which was happening to begin with. The other thing I'd like to remember people of, because I don't want you to go away thinking that I don't think microplastics are important, because I'm a nailed-down environmental toxicologist, and I believe in the precautionary principle. I believe that if you don't know it's safe, you don't go there, yes? And I believe that the whole of history, if I look at tends to support my argument, yes? When somebody says it's safe, it's NIMBYism, these people are trying to scare you. the environmental health profession has usually been correct. But there's a really interesting, strange thing going on around the precautionary principle and microplastics that I cannot wrap my head around. We know there are environmental stressors and environmental toxicants which are killing tens of thousands of people in the United Kingdom and millions of people globally, and we do nothing about it. But when it was microbeads, we were able to get a ban in 2018 almost immediately because microbeads might be tiny, but they are lethal to sea creatures. What's going on? It's like pick and mix issues. This is the precautionary principle applied to something for which there is no evidence, was no evidence of an impact on health at that time, whilst the things which we do have evidence with are not actioned on. And I find that whole dilemma very interesting. And so, conclusion. What can I say in conclusion? We've got to do something about waste. The first thing we have to do is accept how much there is and accept our contribution towards it. Microplastics is part of that problem, but it is only part of that problem. This is a huge global challenge, and it's about time, I think, that we embraced it. In terms of microplastics, I'm only going to say one thing. I would advocate that people working in the field are very cautious with how they present their results, because I think potentially the results are being miscommunicated to the public, and at some point that might result in a breakdown of trust, and I don't think it's going to be beneficial in the long term. But seen in the round, we have to do something to deal with the global waste situation on this planet. Thank you very much.
Thank you very much, Ian. I feel I should be appearing from a pile of plastic before you. It's very interesting that several of the questions which have come in, either from the audience or from outside, have been about policy. Because you've drawn essentially an exponential growth in plastic waste, which we're not resolving, some part of which will appear later on as microplastics in some form. But the growth is massive. And that massive stuff that's going to leach out or become microplastics isn't going away, it's going up. So having thought about this so deeply and actually drawn our attention to the policy initiatives that you might feel, what are your thoughts now on how we might influence politicians not to read the Daily Mail and to do some proper thinking?
Okay, I'm going to imagine that I can influence politicians. Okay?
I know you can, really.
Let's imagine that's the case. I think they're cocooned, really. And look, I often get told that I should roll up to these events and tell you some bad stuff, and then tell you the good news and the positive things we can do about it, yes? I think we do too much of it. Yeah, I think to a certain extent we need to go to the politicians and say, no, this is really bad. No, it does matter if there's a 5-year delay. No, it does matter if there's a 10-year delay. This is an emergency which has to be dealt with at the present moment in time. And then what I would say to a politician is that there are clear co-benefits, yes? Okay? This can be wrapped into a net zero agenda. This can be wrapped into a global biodiversity package. They don't have to be separate things. They don't have to be in conflict with one another. You can look like the good guys and be coherent, yes? And then if it's not at the end of an electoral cycle, you've got a chance that they might listen to you.
So that's a sort of plea for long-termism, isn't it, rather than short-termism?
Yeah, but it's kind of, we're at the point where we need immediate action because the long-term response was required about 30 years ago.
I'm really sorry, I'm going to have to wrap it up because we're over time. Ian, it's been fantastic to hear you talk again. A terrible big problem that we're all facing, if not in the microplastics field. Thank you so much. Thank you.